So now we'll go on to properties of hydrocarbons. So this is mainly in relation to boiling point. So hydrogen bonding, so there's a couple of different things, right? So in class already, you'll have learnt about, dispersion forces, dipole forces, polar forces such as dipole forces, and hydrogen bonding. In terms of boiling points, so the questions that they can ask in terms of the properties are, which one can have a higher boiling point, basically. So will an alcohol have a higher boiling point than an amine, for example? And you need to be able to identify which will have a higher boiling point. And if we're thinking about boiling point, we need to say, defining boiling point, right? Boiling point as a definition is basically the amount of energy required to overcome the bonds between the molecules, right? So the bonds between individual molecules, if we overcome that, we reach this boiling point. So hydrogen bonding between molecules is quite high in alcohols because it's got the polar OH bond. So the H is like the donor and O is like the acceptor. So this means that the melting point and boiling point are higher than their corresponding alkanes, and they're also higher than corresponding alkenes of similar molar mass. So molar mass also plays quite a big quite a big aspect on the boiling point, especially when we get to really large compounds so alcohols, because they're hydrogen bonding, they'll obviously have a higher boiling point than methanol, or let's say propanol. Propanol will have a higher boiling point than propane, but propanol will not have a higher boiling point than maybe an alkane with 50 carbons in the chain. This is because of the effect of dispersion forces. So alkanes are nonpolar, they don't have any polarity in them, so they can only react through nonpolar dispersion forces. So even though they react through very weak dispersion forces, the strength of these dispersion forces can be large enough to overcome the hydrogen bonding. So this is how it happens, right? So we think of the molar mass, right? So when there's a massive amount of carbon chain, right, there's also going to be a lot of electrons within that compound, right? So if there's 50 carbons in the alkane chain, there's going to be a lot of electrons, right? And so these electrons are moving around, and the temporary imbalances in charges caused by these, the electrons, are much greater if the compound has 50 carbons compared to 10 carbons, right? Because the compound with 50 carbons will have a greater electron density than the compound with 10 carbons. And so the imbalance in charge will be a lot greater. And because of this, the strength of the temporary dipoles that are formed are also a lot greater. And if the strength of the temporary dipoles are formed are greater, then the strength of the dispersion forces are also greater. So what happens is the greater the molar mass, or the greater the greater the chain length of a compound, the greater its boiling point is. That's why I mentioned alcohols have a higher boiling point than alkanes of similar molar mass. So if they have a similar molar mass, then obviously an alcohol will have a higher boiling point, because an alcohol can attract or bond using hydrogen bonds, whereas alkanes can only use dispersion forces. Another thing is that alcohols are soluble in water. So the way it works is, if you want to be soluble in water, so water is a polar molecule, so water reacts with itself through polar bonds. And so because of that, you need to be soluble in water, you also need to react with one another through polar bonds. So you need to be quite polar to dissolve in water. And so alcohols up to 3 carbons, so alcohols like methanol, ethanol, and propanol are quite soluble in water due to the hydrogen bonding. And alcohols have a nonpolar and polar aspect. The nonpolar aspect is the carbon chain. So the carbon chain, the 3 carbons there, CH3, CH2, CH2, these carbon chains will be nonpolar, right? The only polar part is the OH bond. So the longer and longer the carbon chain of an alcohol becomes, the less and less polar it becomes, because the carbon chain, the nonpolar aspect, is a lot bigger compared to the polar aspect, which is the OH bond. So C1 to C3 has comparatively a much larger polar aspect than C4. So because of that, C3 will be more polar than C4, and so it'll be more soluble in water than C4. By C4, I mean an alcohol with 4 carbons in the parent chain, so like butanol plus. So C4 plus is anything above butanol. And so anything above butanol, the solubility decreases with size as the nonpolar portion increases. So the nonpolar portion is the carbon chain, and so the carbon chain increases as C4, C5, C6, etc. So the main point that you need to take away here is that alcohols they interact with hydrogen bonding, and so they have quite high boiling points, and we need to supply enough energy to overcome these hydrogen bonds to achieve the boiling, to make it reach the boiling point. And in terms of primary, secondary, tertiary, primary will have a higher boiling point than secondary, which will have a higher boiling point than tertiary. This is because the alkyl groups in primary, or like the alkyl groups in the primary ones are more exposed. So because they're at the end of the chain, or they're primary basically because they're at the end of the chain, the OH group is more exposed, so it can more easily form a hydrogen bond. Whereas with secondary and tertiary, it's less exposed, and so it has a more difficult time forming the hydrogen bonds. And so because of that, its boiling point will be lower. So as the dot point says over here, there's a high extent of the hydrogen bonds forming molecules, and so hydrogen bonding between molecules, and so it will have a higher boiling and melting point. So that is the properties of an alcohol. Now we'll go through a little bit more. So now we'll go through the enthalpy of combustion. So in class, you'll do a prac where you burn a few alcohols under some water and measure the temperature change of the water. And this is trying to calculate the molar enthalpy of combustion and we're trying to find how the molar enthalpy of combustion increases as the alcohols get bigger. So that's essentially the gist of the prac, but what you need to remember is that the molar enthalpy of combustion will increase as the alcohols get bigger. And it kind of makes sense because the larger molecules will have more bonds, and so when you're breaking more of those bonds, you'll release more energy, and so because of that, you'll get more energy per mole. And the molar enthalpy of combustion is given by delta HC, which is equal to negative MC delta T over the moles of fuel that you burned. So yeah, if you did physics last year, then you would know MC delta T. You'd probably know that in chemistry as well, and you just divide it by the moles of fuel that you burned. So let's go through this question now. Question 17. Students were asked to perform a first-hand investigation to determine the molar heat of combustion of ethanol. The following extract is from the practical report of one student. Calculate the molar heat of combustion of ethanol using the student's data. So let's use the formula, right? So we have Q equals MC delta T, M equals grams of water, C equals 4.18, delta T is the change in temperature, and Q will be in joules because we're using 4.18 and grams. So we need to later then convert it into kilojoules and then divide by the number of moles. So let's look over here. So Q equals MC delta T. M is 250. We have over here mass of water over here is 250. C is 4.18. Delta T is, so the final temperature minus initial temperature, 59 minus 19. So we have 40 degrees. So then Q, when we multiply all this together, is 41.8 kilojoules. Now we need to find the mass of ethanol used. To find a mass of ethanol used, what we do is we get the initial mass of the burner and the final mass of the burner, and we minus them together to find the change in mass. And that change in mass is the amount of ethanol that will have combusted. So if we do that, we get 2.3 grams, and we can find the molar mass of ethanol because now we know what ethanol is. So C2H5OH, or it's just CH3C CH2OH. So we know what ethanol will look like now because we've done IUPAC nomenclature. And so we can find the molar mass of it, and we can, by doing N equals M over M, we can do 2.3 over 46.068 to get 0.0499, and that is the moles of ethanol burnt. So now all we have to do is, we need to find kilojoules per mole. So we know the kilojoules, 41.8, and then we divide it by 0.0499 to get 837 kilojoules per mole. Something that's very important here is you need to be able to know whether it's positive or negative. So although this says 837 kilojoules per mole, the enthalpy of combustion, right? It's combustion. So we're releasing energy into the surroundings. Because we're releasing energy, technically the system itself is losing energy, right? Because it's losing energy to the surroundings, we're releasing energy. So because of that, the answer actually has to be negative. So it's negative 837 kilojoules per mole because it's the enthalpy of combustion. We're losing energy to the surroundings. The system itself is losing energy because we're releasing it to the surroundings. Combustion is exothermic. So it's negative 837 kilojoules per mole. That's something that you should always remember when you're doing enthalpy of combustion. The answer will always be negative. So now let's go through properties of other hydrocarbons like aldehydes. So they generally have an unpleasant odor, and the carbonyl group is polar due to the high electronegativity difference of the C and the O. And the aldehydes, because of that, they can attract through dipole-dipole forces and dispersion forces. They can't interact through hydrogen bonding though, because they don't have a hydrogen bonded to an oxygen or a hydrogen bonded to a nitrogen. And in general, because the CO bond is at the end of the molecule, the compound itself is less polarized than if the C double O bond or the carbonyl group was in the middle of a ketone. And because the aldehyde is less polarized, it can interact through polar bonds less frequently or less strongly than a ketone. Because of this, they have lower boiling points and lower melting points than their ketones. So similar to alcohols, aldehydes with 1 to 3 carbons are quite soluble in water. So methanol, ethanol, propanol are quite soluble in water because they're capable of hydrogen bonding with the water. But C4 plus, so anything like butanol, pentanol, etc., they're less soluble in water due to increasing proportion of the nonpolar section. So as the melting point and boiling point increase, as the melting point and boiling point increase as chain length increases, it becomes less and less polar, and it becomes more and more nonpolar. And so as the carbon chain increases, aldehydes become less and less soluble. And then the final point, melting point and boiling point, these increase as chain length increases, just like I mentioned before. So as the chain length increases, the strength of dispersion forces that it can form increases as well. And so because of that, the melting point and boiling point increase. All right, now we'll go on to ketones. So ketones have in contrast to aldehydes. So aldehydes have an unpleasant sharp odor. Ketones have a pleasant and sweet odor. So the carbonyl group is polar due to the high electronegativity difference of CO bond, again, just like aldehydes. Ketones are capable of both dipole-dipole and dispersion forces. And in opposition to aldehydes, because the C double O bond is in the middle or more towards the middle of the molecule, it is more polarized than the one on the end of the molecule in the aldehyde. Because of that, because it's more polarized, it will have higher melting points and boiling points than the corresponding aldehyde. So in an exam question, you can't just say that because it's more polarized, it's going to have a higher boiling point. You need to be able to expand on this. So because it's more polarized, it can, like the strength of, it can form stronger polar bonds. And by forming these stronger polar bonds, it will be able to have a higher boiling point because we'll need to supply more energy to overcome these like stronger polar bonds. And just like aldehydes, C1 and C3 are very soluble in water. C4 plus are less soluble in water due to increasing proportion of the nonpolar section, because as the carbon chain increases, the nonpolar section increases, and so the compound itself becomes less and less polar, and so less and less able to dissolve in a polar solute like water. However, as the chain length increases, the melting point and boiling point do increase as well. And now we go into carboxylic acids. So carboxylic acids, COOH. So the functional group for a carboxylic acid is the C double bond O bond and a very polar OH bond. So each of these like bonds can form 2 hydrogen bonds. So the COOH bond can form 2 hydrogen bonds. Because of that, it will automatically have a higher melting point and boiling point than alcohols. Same with aldehydes and ketones. It will have a higher boiling point than all 3 that we've talked about so far. So obviously, it will have a higher boiling point than an alcohol, an aldehyde, and a ketone of respective molar masses, so of a molar mass close to it. So it has a high melting point and boiling point, and the only homologous series with melting points higher than carboxylic acids is amides. So amides is the only one that has a higher melting point and boiling point than carboxylic acids. So just like alcohols, aldehydes, and ketones, C1 to C3 are quite soluble in water because it's quite polar at that point. But it gets less soluble after that because as the chain length increases, it becomes more and more non-polar, and so more and more less soluble in a polar solute like water. So yeah, melting points and boiling points increases with size, and the very important takeaway here is carboxylic acids form a stable dimer structure, and this stable dimer structure allows it to like form a very strong very strong intermolecular bonds with itself. And so because of that, we require a lot of energy to overcome the stable dimer structure, the bonds within the stable dimer structure. And so it gives it's a very strong or very high melting point and boiling point. The reasons why amides have a higher boiling point than carboxylic acids is because amides interact through another keyword over here, a network of hydrogen bonds. So the keyword over here is stable dimer structure. You always want to include that if you're talking about the boiling point of a carboxylic acid. And if we're comparing with an amide, the reason why amides have a higher boiling point is because of the network of hydrogen bonds within there. So let's look at amines and amides now. So amines, C1 to 2 are gas at room temperature, C3 plus are liquid. So two highly polar NH bonds in primary amine mean they can form two hydrogen bonds. So they have very high melting point and boiling point, but not as high as amides since they also have a C double O bond. So amides can form more hydrogen bonds. And just like before with all the compounds, melting point and boiling point increase the chain length for a similar reason, and is also quite soluble in water. And this decreases as chain length increases because the non-polar proportion increases as well. So amides. So above C1, it's solid at room temperature. So yeah, it's quite, they're quite like, they have very high melting point and boiling points. And a primary amide has a C double O bond and two polar NH bonds, which make it capable of hydrogen bonding. And this means amides have the highest melting point and boiling point of all homologous series. So out of all the organic compounds that we've learned so far, amides have the highest boiling point. And they're the only one with a density higher than water. And just like with all the other compounds, the melting point and boiling point increase with chain length. Yeah, and they're soluble in polar substances, but this decreases with chain length again because the non-polar proportion increases. And just like I mentioned before, the key word here is that they form a network of hydrogen bonds. That's what allows it to have a higher melting and boiling point than carboxylic acids. So yeah, now we go through alkanes. So let's go through unbranched alkanes. So alkanes, they are, let's take unbranched alkanes. So let's go straight linear line alkane, so just an alkane in a straight line. So they can only interact through dispersion forces because they're all nonpolar. So the only way that they interact is through temporary imbalances in charges that occurs within like the molecule itself that causes it to form temporary dipoles. And these temporary dipoles will be attracted to other temporary dipoles between the alkanes, and this will cause it to basically react with or basically interact with one another through dispersion forces. So this is how it interacts. So it's quite weak, and so because of that, it has quite a low melting point and boiling point. It gets even worse if it's branched. So if it's branched, there's a lower boiling point and melting point because the molecules cannot pack tightly together, and there's also a smaller contact area between the molecules, and so it'll have an even lower melting point and boiling point. And these branched alkanes will have a lower density as well because they can't pack together as well as these branched or these unbranched alkanes. So the branched one will have a lower density than the unbranched ones because the unbranched ones can fit together quite nicely. Alkenes and alkynes. So alkenes are more reactive than alkanes due to the electron density of the double bond, but they do have a lower melting point and boiling point than their corresponding alkanes. And this is due to having fewer hydrogens, so they have fewer electrons, which means they have weaker dispersion, or they have weaker temporary imbalances in charge, which leads to weaker temporary dipoles being formed, which leads to weaker temporary dispersion forces. So it's like a cause and effect type thing. Alkynes, so they have a lower melting point and boiling point than the corresponding alkenes, essentially with the same number of carbons, because once again, fewer number of hydrogens than alkenes, so fewer electrons, fewer temporary imbalances in charges, fewer temporary dipoles forming, fewer electrons, so weaker temporary dipoles, weaker temporary imbalances in charges, so weaker temporary dipoles forming, and so weaker dispersion forces. But once again, as the molecular mass increases, the melting and boiling points increase as well, because obviously the temporary imbalances in charge will also increase as the electron density increases. And it'll also become, these are also insoluble in substances, insoluble in water, because water is a polar substance, and so this unpolar substance will be very insoluble in polar substances because it can't react with one another through polar bonds. So yeah, the general gist is alkanes have a higher boiling point than alkenes, which have a higher boiling point than alkynes. But it's swapped around in terms of reactivity. Alkynes have a higher reactivity than alkenes, which have a higher reactivity than alkanes. And because alkanes are because they're saturated, they react through substitution reactions. So what they do is, for for a reaction, a substitution is essentially they take away a hydrogen and replace it with something else. For alkenes and alkynes, they go through addition reactions where they break the double bond, and then they open the double bond into a single bond, and then they have they have to fit the rest of the gaps in the carbon, and so more molecules come to fit those gaps. So yeah, that's kind of the visualization of the difference between a substitution and an addition reaction. So quick bit on haloalkanes. Haloalkanes are capable of dipole-dipole bonding due to the polar CX bonds that they have, because halogens are very electronegative. And so they're quite capable of dipole-dipole and dispersion forces as well, meaning that their boiling point and melting point are higher than their corresponding alkanes. And they're also slightly soluble in water due to this dipole-dipole interaction that they can have, so the polar interaction that they can have with the water molecules. So they're more soluble than alkanes, alkenes, and alkynes, but way less soluble than everything else that we've learned about, because everything else that we've learned about is quite polar. So yeah, homologous series, basically these organic compounds, the trends, right? So melting point and boiling point increase as the molecule gets larger. So an increase in the number of electrons means temporary dipoles are stronger and more frequent, so dispersion forces are stronger. And then solubility decreases as carbon chain gets longer. That's because as the carbon chain gets longer, the nonpolar proportion of the compound keeps increasing until the compound becomes less and less polar. And as it becomes less and less polar, it's unable to react, in terms of the whole compound itself, it reacts less and less using polar bonds with water, and so it becomes less and less reactive or soluble in water. And also larger liquid molecules are more viscous than smaller liquid molecules. So from highest melting point to lowest melting point across all the organic compounds, we have amides, carboxylic acids, alcohols, ketones, aldehydes, amides, carboxylic acids, alcohols, ketones, aldehydes, amines, haloalkanes, alkanes, alkenes, and alkynes. That's just a general gist. If you understand the reasoning behind it, so with amides, the keyword is network of hydrogen bonds. Carboxylic acid, the keyword is the stable dimer structure. Alcohols, the keyword is the hydrogen bonds, etc. So that is kind of the trend. If you remember those keywords, then you should be okay. So let's look at this question right here. So it's a 5-mark question, so obviously we'll have to be writing a lot for this question. So the boiling points and molar masses of 3 compounds are shown in the table. We have acetic acid, butanol, butyl acetate, and those are the 3 compounds. They have different molar masses, very different, so varying from 60 to 116, but quite similar boiling points, right? Explain why in terms of structure and bonding of the 3 explain why these trends follow in terms of structure and bonding. So looking at this question, the first thing that I'd recommend you doing is whenever you introduce a compound, always put their respective boiling point in brackets. So this shows the marker that you're actively referring to the data that they provided. So if you're saying butyl acetate has the lowest boiling point, full stop. Instead of saying that, say butyl acetate has the lowest boiling point of 116 degrees Celsius to show the marker that you're actively referring to the table and using making use of the information provided. That's just a side note. The main thing that I would look here is, look at the functional groups, right? One is acetic acid, so carboxylic acid. Obviously, it should have the highest boiling point here because there's no more amides. So we have butanol, so okay. Alcohol, so it should be lower boiling point. And we have butyl acetate, so that is an alkane. Sorry, no, butyl acetate is not an... Oh, actually, it is an alkane. So butyl acetate is an alkane, so it should have a even lower boiling point. So looking at this, right? Why do they have similar boiling points? Acetic acid, carboxylic acid should have a significantly higher boiling point than an alcohol and an alkane. Now, the only difference here that I can see is the molar mass, right? The molar mass increases significantly, going from 60 to 116, and then it clicks, right? So the molar mass is the reason why these boiling points are very similar. So what I would first say is, I would first talk about molar mass and how it does or doesn't impact the boiling point significantly. So in this question, it does impact the boiling point significantly, right? So if looking here, right? So what I would say is the molar mass, the molar mass affects the boiling points of these subjects, of these compounds, significantly. And then I would explain how, the electron density, so the greater the molar mass, the greater the electron density, the greater the temporary imbalances in charges that can occur, which means the greater the temporary dipoles that can form, and greater the temporary dispersion forces that can form. And due to these greater temporary dispersion forces, the amount of energy needed to overcome these greater temporary dispersion forces increase, right? And because of that, its boiling point also increases. So the reason why it's very similar is due to the increase or the significant increase in molar mass. But, obviously I have to explain it a little bit more. So then I would say introduce a difference so after talking about molar mass, I would introduce a difference in functional groups and how that makes a difference. So I would say acetic acid has, how it would interact through the stable dimer structure. I would draw a diagram showing the stable dimer structure. I would show the hydrogen bonds between, carboxylic acids. Same with alcohols. I'd say how they interact through hydrogen bonds, etc. And then I would say, despite the general trend of carboxylic acids having greater boiling points than alcohols, and alcohols having greater boiling points than alkanes, in this scenario, they have very similar boiling points due to the effect that molar mass has on it. So the increase in molar mass has this effect, and then I would end the question there. So that's how I would answer it. I would introduce the key concepts first to show the market that I know what I'm talking about, and then I would specifically relate it to the question to answer the question.